at some of these examples. So the first one, we're given a function there to integrate f of xy, and f of xy is the exponential of the quotient x over y. And we're being asked to integrate that over the region D. And I describe D as the region bounded by these three curves. So x equals y cubed, x equals y, it's the straight line, the red line, and x equals 2. So x equals 2 is the vertical line located at x equals 2. The blue curve is x equals y cubed, and the red line is x minus y. So that defines this. Those three curves form the boundary of this kind of triangular looking region here in the middle. Okay. So what we'd like to do then is integrate this. Okay. Question 1. Yeah, let's integrate this. Now, this integral I will be the double integral of e to the x over y. And I have to make a choice about what I'm going to integrate it with respect to first. So I'm just having a bit of a mind blank at the moment. So I've got a choice, you know, here I could either go dx dy or I could go dy dx. So which of these will be the easier one to integrate? Well, see, at the side I can do that. If I know integrating x over y dx, that would just come out as y e to the x over y. So I should make the inner integral be with respect to x. Okay, because that integral is easy enough to carry out. If I had to first integrate with respect to y, then that might be a bit trickier. Integrating e to the x over y might be a bit more complicated to handle. Okay. So I should go integral dx, integral dy. So then you come to decide on the limits of integration for this. Okay, so you look at where the region is, and you see that the region lies between the y values 1 and 2. Okay, because this top vertex here, that top vertex there where the mouse is pointing to, is the point with coordinates 2, 2, with the intersection of x equals y with x equals 2. And the lowest that the region goes down is equal to, is this point down here, which is at y equals 1. Okay, so we have to go integral from 1 to 2 with this. So I have this region like this, and I'm going from y1 to y2. So then you imagine a typical value of y in the middle here somewhere. For a typical value of y in this range, what are the limits for x? Sorry, hang on. Sorry, I'm just having a bit of a mind. X on the outside integrated with respect to y. Okay, we just have to be very careful. Yeah, so this example is is trickier than I originally thought. See, the curves look like this. This curve is the x equals 2 curve. This curve is the y equals x curve. And this curve here, the bottom boundary, that's the y equals, no, that's the x equals y cubed curve. The x equals y cubed, or think of that as y equals x to the third. Now we've agreed to make the outer integral be with respect to y. So y is varying between the limits 1 and 2. Okay, this is the lowest down that y goes, which is y equals 1. And this is the highest that y goes here, which is y equals 2. But what's going on here is we've got different kind of behavior for the x limits. Because for these lower values, for those lower values of y, the boundary between the limits for the x variable fall on the curve y equals x and x equals y cubed. Okay? And it's only when you get up to this point, what's the height at this point here, this other vertex of the triangular region? Well, that's the intersection between x equals 2 and x equals y cubed. So this is the cubed root of 2. So this is 2 to the power of third. So the cubed root of 2 is a little bit above 1. Yeah? So for values of y between 1 and the cubed root of 2, x, the left limit of x is given by the x-coordinate at the point on the curve y equals x. The upper limit of x is given by the point on the curve x equals y cubed. From between the third root of 2 and 2, it's different. There, the lower limit of x, well, it's always on the curve x equals y, but the upper limit then is always x equals 2 for the rest of the integrals. So what was causing me to pause and have trouble thinking there was the fact that you can't get it as a single integral. Okay? Because there's no single description. Well, actually, there is one for the bottom, because the x limit is always starting at y. But there's a different, sometimes the upper limit for x is on the curve x equals y cubed. The rest of the time, it's formed by x equals 2. Okay? So, yeah.
So, I don't understand. Why were you confused?
I was confused because I was trying to write it in a single thing like this. But what we need to do...
That's not single.
No, yeah, but just as one double integral. Now, instead, we'll need to split it up into 2.
You mean that integral?
Yeah, take one double integral and add it to another one, which I'm going to show to you now.
You know the second
yeah.
integral, shouldn't it be 0 and 2, shouldn't it?
No. If you made these limits 0 and 2, you'd just be integrating over a rectangle.
Or something.
But that's not what we're asked to do. The question asks us to integrate over the region bounded by these 3 curves, which is this inner triangle-like region in there. That's what we're trying to integrate over. Yeah. Okay. So I go from 1 up to the cubed root of 2. Sorry?
Equals, not that.
Yeah, I know. Equals, because that's what it is. I'm going to re-express this as the sum of 2 double integrals. Just watch and see it. So we're integrating first for y between 1 up to the cubed root of 3, and that's the red shaded region here. So for there, the x always begins at the value y, and it finishes at the value y cubed. And we're integrating e to the x over y dx dy. Okay. But then I need to add on integrating over the second part. And that's going from y on the cube root of 2 all the way up to 2 itself. And there, the x strips, they start at the point on this curve, and they always go up as far as x equals 2. So again, that's starting from y and just going up to 2. And then this is e to the x over y dx dy. So in fact, there's no problem with this lower limit. The lower limit for x is always y, but the problem is the upper limit. See, some of the time the upper limit is y cubed, and some of the time it's just 2. Okay, when I first set out this example, I didn't think we needed that subtlety, but it's a good illustration. Okay?
So the first thing is
Yeah. The first thing, yeah. So, but except I can't finish this expression up here because some of the time I need one expression of y up here, y cubed. The rest of the time I need just x equals 2. So I can't finish that. Can't finish that expression.
surely you have to flip the order you do it.
Yeah, but if I flip the order I do it in, yes, if I flip the order I do it in, then the description of the region will be simpler. However, I'll struggle, actually doing the integration will be a little bit harder, because I'll have to integrate e to the x over y first with respect to y. And it's not so easy to see how to do it. So then we can integrate these out. So I mean, if I call this one I1 and this one I2, okay, we could calculate those out separately. So I1 then, leaving the outer integral unchanged, performing the inner integral, so we'd have y e to the x over y, and that must be evaluated at x equals y and x equals y cubed. And we've got y here. So when we put x equals y cubed, then what we'd see here is y e to the y squared minus y times e dy. Okay, but now we've just got a straightforward one variable integral with respect to y. And we can integrate this. So integral of y times e to the y squared, well, that's a nice one. So you can do that by substitution, substituting u equals y squared. And you'll see it's equal to 1/2 of e to the y squared. And then this is simply y times e, so this will be y squared over 2 times e. And these get evaluated at y equals 1 and y equals 2/3. Sorry, yeah. Okay. So you'd be ready to do the final evaluation there, just substituting in these constant limits for y.
So why have you divide the y squared? Yeah.
This one here.
So the first one.
This one? Well, if you take this and differentiate it, you see you get back to y e to the y squared. Yeah. Okay. So this can now be evaluated. As can I2 as well. Okay. Sorry, that example threw me a little bit. When did I put it down right? Yeah, question. How going from here to here? Well, it's so if you just do it in reverse there, if you take d dy of 1/2 e to the y squared, well, you're differentiating an exponential, so it will be the same exponential, but then you're doing the chain rule, so you have to multiply this by the derivative of the argument of the exponential, so it could get multiplied by 2y. So that gives you your y e to the y squared, which is what we have. So I skipped it up, but you could do it by integration by substitution. If you let y squared be u, then when you change the dy to du, it will cancel the y there and bring you to that final integral. Can now be evaluated. Yeah, so I'm not going to go ahead and do it because it's just putting in the values and working out the value on your calculator. So, yeah. Okay. So let's go to another example. No, it's not the final answer, but it gets you to the stage where it's just substituting in those values for I1, and then you can go back to I2 and evaluate that. But I'd mostly like to deal with showing you examples of dealing with the regions and setting out the limits and so on. Okay. So let's look at this example 2, question 2. So here we want to integrate f, which is just the product xy, over this triangle shape. So just the double integral over this triangle. So you're told the triangle has vertices 0, 3, 1, 1, and 5, 3. So that's a plot of how the triangle looks. So then you have to think about how you'd plot this out. So you need to get descriptions of those boundary curves. You need the precise equations defining these. Okay, so the top line is the easiest one. That's y equals 3. Okay, so it's joining these points 0, 3, 5, 3, and this one down here. What's that? 1, 1. Okay, so the top curve is clearly y equals 3. And these other curves, well, they're both lines, so they should have expressions. You know, y equals mx plus c. So what's this one over here? So this first one over here, let's call this C1 for the sake of it. So C1 has an equation y equals mx plus c. Well, the c is equal to 3 because the c should be the intercept when x is equal to 0. And the slope, we get the slope, you just divide the y difference by the x difference. So the y difference is 2, and the x difference is minus 1. So slope minus 2. Yeah. So this seems to be y equals minus 2x plus 3. So when x is 0, you get plus 3. When x is 1, you get 1. Yeah, that's right. So this one, C2 will have a y equals mx plus c. So the m, the slope is going to be the y difference, which is 4, over the x difference, which is 2. So the slope is plus 2. And what's the intercept? Sorry, my brain really isn't working today. I'll just have to do simultaneous equations, won't I? So 3 equals 2 times 5 plus c. So c is minus 7. All right. That doesn't look right, does it? Sorry, my brain really isn't. Sorry.
That is a half, not 2.
Why did I get 2? Slope is y difference over the x difference.
2 over 4.
2 over... y difference. Yeah. I said it right. Thank you. So the slope is 3 minus 5 over 2, which is 6 minus 5, which is 6 minus 5 is 1. So c is a half. That seems a lot more reasonable. Sorry. So this curve here is y equals a half x minus a half plus a half. Phew. Yeah. Okay, so plenty of places to go awry here. But now at least we have the precise descriptions of each of the parts of the boundary. So we can write down one of these integrals. But what order are we going to express it as? See, if we choose the wrong order, then like the previous example, well, not the wrong order, but if we choose one order, like the previous example, we'll need to produce 2 double integrals, you see. Because if we integrate first with respect to x, so if we make x be the outer integral, then the inner integral, you see, sometimes the vertical strips start on this line and end at the top, but then the rest of the time they start on this line. So as x goes from the lower limit of 0 to the upper limit of 5, the curves forming the boundaries for the y strips, they change. See, some of the time it's C1, and then the rest of the time it's C2. So that would require 2 double integrals. Whereas if we integrate first with respect to y, it'll be a lot easier. So if we look at the y limits, we make the outer integral be with respect to y. You look at the region, and you say, where, with regard to the y variable, is the region? Well, the region stretches from y equals 1 up to y equals 3. And then for a typical value of y in that range, is a typical value of y, we want to integrate the x variable from this lower limit of x here up to this lower limit, up to that upper limit of x here. Okay. So we want to go from this lower limit here to this upper limit here. Okay. So those should be given to us from the boundary curves. Now we'll have to invert them, won't we? So at the moment they're expressed as y equals a function of x. We'll have to get them now as x equals a function of y. So the lower limit for x comes from here. So that's going to be y minus 3 over minus 2. That's the lower limit for the x variable. The upper limit for the x variable comes from here, which is y minus a half, and you have to multiply it by 2. So that's 2y minus 1. Okay. So the lower limit for x and the upper limit from x come from inverting the equations y equals mx plus c. For the lower, for this curve C1, this is the one going into the lower limit here. So C1 is going in here, and C2 is providing this back there. Okay, but now we can proceed and do the integrals. Got integral 1 to 3 dy. Well, integrating this x times y with respect to x, this is going to be 1/2 x squared y. And then that gets evaluated at, remember these are limits for x. It can often help to put down x here. X equals y minus 3 over minus 2. And the upper limit is x equals 2y minus 1. Okay. So we can substitute these things in for y, and what we'll get is just a polynomial in y. This will be 1/2 2y minus 1 all squared times y, and then minus 1/2 y minus 3 over minus 2 all squared times y. Okay, and that's just a familiar integral of this function of a single variable, and it's just a polynomial function. So we could multiply that out and evaluate that as well. Any questions about that? You could also have written it down in the other order, making the inner integral be with respect to y and the outer integral be with respect to x. You wouldn't have to invert these I think I'll just put that down. So you could say alternatively, we could write this integral as, so make the outer integral x and the inner integral y. Well, where is the triangle with respect to x? With respect to x, it's between 0 and 5. Yeah, but we have to first just go from x from 0 up to 1. And when we go from 0 up to 1, we want to talk about vertical strips across the region. And these vertical strips always end at y equals 3, and they begin at y equals minus 2x plus 3. Yeah. And then plus the rest of the integral, this time from x equals 1 on up to 5. And there the y begins at 1/2 of x plus 1/2. And again, it ends at 3. So that's how the same integral would look in the other order. But this time now we need to write it as two double integrals, okay? Because we have different functions giving the lower limit for the y variable over different parts of the x range. Okay? Okay, and you can check that this evaluates to the same answer as before. Okay, so here's a couple of examples for you to try. So here, I'm not worried about the function we're integrating. We just want to get some practice dealing with the regions. So these previous two examples kind of gave you the geometric description of the region, and then you have to formulate the limits. Whereas here, you're given the integrals in one way with the limits there. Now, the first one, notice, is dx dy. The second one is the other order, dy dx. But for each of them now, we'd like to reverse the order of integration. So re-express those integrals as integrals with the opposite order. So the first one we want to write as integral dy dx, and the second one we want to write as integral dx dy. but we'll have to go via a nice sketch of the region. Why don't you take a few minutes to look at those now, and I'll go through the answers in the yeah. The rest of the first page. Okay, so do discuss this, of course, with your neighbors, and you'll want to get a nice plot or a nice sketch of the region. Any questions about the previous example or anything I could answer for you?
Y to 0 and Y to 2.
Hang on. Yep. Yeah. Well, that's what I'm asking you to do, but you have to handle what happens to the limit. You have to go. You have to first sketch the region that you're integrating, and then see about how it would look when you change to your integration. So the first example, I've got a little sketch like this. So I've sketched my two curves here. I've got the y squared equals x curve. Well, first of all, I'm interested in the region for y between 0 and 2. Because the outer integral is the y integral, and it goes from y equals 0 up to y equals 2. So the region is somewhere in this horizontal band between y equals 0 and y equals 2. And for a typical value of y, the lower limit for the little horizontal strip is given by the curve x equals y squared. So I've sketched that out here. So this point at the edge here will be the point with coordinates x equals 4 and y equals 2. And the upper limit for these horizontal strips is given by the straight line x equals 2y. So again, that goes through this point, x equals 4, y equals 2. Okay? So intermediate values of y, we're integrating, see, to cover this region. That's what the integral is So if I want to reverse the order, so this, what I'm looking at here is the integral from y to 0 to 2, and then y squared to 2y of f of xy dx dy. So if I want to write that in the opposite order, if I want x to be the outer integral now, so you always decide on these limits by working from the outside in. So you look at the region, this shaded region, this red region here. Where is it located with regard to x? Well, you can see it's located between 0 and 4 for x. Then you're asking yourself, well, for a typical x value in that range, I'm talking about these vertical strips. So the lower limit for y, given the value of x, the lower limit for y would be square root of x. And the upper limit for y would be, well, if you know the value of x, the upper limit for y is going to be a half x. Okay? So that's how the integral would transform. I mean, as you get more practice with these, you may be able to just reverse the order and invert the relationships between the variables kind of in your head, so to speak. But I definitely recommend going via a sketch of the region. So you're it's a lot easier to see what's going on when you look at the sketch of the region. Okay. So the second example here, we have time. Well, at least we've got time to sketch the region. So we're going from a half up to 1, and that's on the x variable. And then we're going x cubed up to x, and that's for the y variable. So to sketch this, I'm interested at what's going on between x equals a half and x equals 1. And I've got two curves, y equals x cubed and y equals x. So y equals x cubed will be coming up here, something like this, and then it'll do this kind of thing. So that's 1 there. That's y equals x cubed. And we've also got y equals x. Now that will be above this. That's just the straight line. Sorry. It's y equals x there. Sorry, it becomes less straight looking when it gets up here. It should be the straight line, y equals x. So for a given x value, the y strip begins, the lower limit is x cubed and the upper limit is x. So the region being integrated over is this region here. Again, this looks like one of the tricky ones, which is going to need more than one double integral to handle when the order is changed, okay? Because there's this significant point here. If I want to express this going the other direction, the other order, so I want to make y being the outer integral, well, the region begins at y equals 0, but the region does go all the way up to 1. However, for this first, no, sorry, excuse me, scratch that. It doesn't begin at 0, sorry. The region begins at y at this lower limit here. So what's that value? That's the point a half, and the y is the cube of x, so that's going to be 1 over 8, sorry. That's the cube of a half, so that's 1/8. But then I should only go up as far as y equals a half for that first example, because for that part of the region, that lower part of the region, the horizontal strips always begin at x equals a half, and then they end on the curve y equals x cubed. So if y is given, x is the cubed root of y. So this double integral covers the region, the part of the region there that I've hatched with the horizontal strings. But the rest of it then has to be handled separately. So separately then I go integrating from 1/2 up to the point 1 dy. And then for those values of y, for the values of y in the upper part, the lower limit for x is given by the point on the straight line. So the lower limit is actually y. And the upper limit is again given by the point on this curve, y equals x cubed. So if you know y, then you know x is the cubed root of y. Now that's why I say go, when you're sketching these regions, it's very much helpful to do a sketch. I find it extremely awkward or extremely difficult to just go, if I'm just looking at the description of the original integral there, and inverting the relationships and realizing you need a sum of two double integrals for it. You definitely need to go via a sketch for that one.